Hey, it's Dr. J, back with more calculus today. Limits, continuing the lecture on limits. Today we will dig right into the graphical and the numerical methods of evaluating a limit or calculating a limit or determining a limit. Sometimes I'll say find the limit. I got started a little early today and just wrote down the two definitions that were in the introductory video. I wanted to encapsulate them in a nice formal sort of textbook fashion here. So just a quick review of the limit. Again, this is the intuitive definition. This is not the precise definition, which we will get into later. By intuitive, we mean that we use sort of intuitive words like near. So the limit of f of x as x approaches c is L if f of x is near a real number, right? And again, we ran into this in the intro. It must be one real number. I could write one, but I just say a. So a real number L when x is near c. And this is my cloud of intuition. Since this is the intuitive definition, near means close to, but not necessarily equal to C. All right, so that's what we mean when we say near. Close to C, but not necessarily equal to C. Okay, so that's the definition of a limit. We'll do quite a few examples today. Then I also want to distinguish between what a limit is versus what the value of a function is. All right, they sometimes are the same, and we'll see that in today's lesson, but they sometimes are different. They have different definitions. The value of a function, f of x, at x equals c, okay, so there's no near. This is actually equal, is f of c. Yeah. Now, even though we write f of c, what this ultimately will end up being is a point if c is in the domain of the function. So in other words, the point must exist. All right, it can't be a hole. It has to be a dot. Yeah, or a closed dot. Yeah. Again, I made a lot of synonyms yesterday, or I used a lot of synonyms for what it means to be existing, yeah, for the point to exist. And so the point is c comma f of c. We do have to use ordered pair notation, so parentheses. And then I'll make a note here. F of c is a y value obtained by plugging in c. So, you know, you have the whole input and then the output, which is why the value must be in the domain, because if it's not in the domain, then you can't plug it in. And then if you can't plug it in, then you can't get something out, and then this point would not exist. All right. So that's what it means to be a value of the function. All right, well, take a quick look at that. Maybe screenshot it, or you'll also see these definitions in the textbook. Let's go ahead and do some examples. So suppose we're given a function, y equals f of x. And let's suppose 6 is equal to f of 2. And the limit as x approaches 2 of f of x is 8. All right, so we're using both of these definitions here. This is the value. and this is the limit. So we are supposing that they both exist. So that's an assumption that we make at the beginning of this problem. All right, so let's see what this would look like graphically. I really only need the first quadrant, but I'm going to go ahead and put them all out here. I might use them more quadrants later in this last lesson. Tomato. So, what do we got? All right, so we've got 2. X is 2. We have y is 6, so y is 6, and x is 2, so 1, 2, 3, 4, 5, 6. This point exists. Yeah, it's given. It's in the domain, we're assuming. So that is a solid dot. All right. And then we have the limit, L. So this is our L. Okay, and the limit is like a hole. Yeah, so we're getting close to x equals 2. This is what we mean by near. Yeah, this is also called a neighborhood. And so as we get close to 2, the y value is close to 8. Yeah. So we have L is 8, and then we have f of 2 is 6. So we have the limit and the value, and they do not necessarily agree with each other. Now, in this particular graph, because we were starting with just 2 assumptions, we don't really know anything else about the behavior of the graph. So the graph could be something like this. We don't know. Right? Or it could look like this, I mean, there's so many possibilities for what the graph could look like. We can't really assume that. Based on the information that we have, we just know that near x equals 2, we know the way the graph is behaving, but we don't know what's happening away from x equals 2. Not in this introductory example 1. We would need more information to determine what's going on outside. All right, so that's sort of the summary of the 2 concepts in today's lecture. The rest of the examples today will either be a graphical example or a numeric example. Since I already have my graphing board out, let's just go ahead and summarize. Oh, wait a minute. Hold on. Before I do example 2, let's summarize the vocabulary. So we're going to say the limit as x approaches, just before I erase all this, approaches 2 is 8. We're going to say f of 2 is the value of f of x at x equals 2. And we're going to say 2, 6 is a point on the graph. So just a quick summary of the important terminology and the vocabulary that we'll be using throughout the lecture today. So we say the limit is 8. The value is f of 2. Which turns out to be 6 in this problem. All right, it's not always going to be 6, obviously. And that's a point on the graph. So we have the limit, the value, and the point. Those are the three sort of takeaways before I erase all this stuff. Okay, so example 2, suppose we're given the graph of the function y equals f of x. So when we're given a graph, we assume that all of the information that we need for that particular problem is shown in the graph. Counted wrong. Doesn't really matter, but so there we go. There's our graph. Maybe I could scoot it up just a little bit. Give myself a little more room to work. I love these magnetic boards. If you watch some of my older videos, I tried to actually draw the X and Y axes myself, and it got pretty messy, so special thanks to Amazon.com for sending these next day. All right, so let's go ahead and assume that this is a unit scale. If it's not a unit scale, I would specify that otherwise. But just to be absolutely clear, that's 1, 2, 3, 4. So that's our critical value. That's our C. All right, and 1, 2, 3, and 5. Oh, and let's go down here into quadrant 4. That'll be -2 for the y value there. So we got a lot going on here. It's a little bit more busy. Okay, so let's find the following. Let's start with the limit. Guess we'll call this part A. The limit as x approaches 4 of f of x. Okay, so look what's going on here. As you get near 4, and again, you don't have to draw these little neighborhoods here. There are 2 possible real numbers. There's -2. Yeah, the function is near -2. It's also near 3. Okay, now it's not near 5 because that's the value of the function. That's what it is when it actually is equal to 4, which is sort of intuitively what we mean when we say when we're near 4, the function is either near 3 or it's near -2. When you actually get to 4, then it becomes that dot at 5, or the solid or closed point. So this limit does not exist, dne, because there is not one real number in which the graph of the function is getting near. And then find the value, f of 4. Well, that does exist. Yeah, that's 5. So this time the value of the function exists, but the limit does not exist. All right, they're all going to be sort of very similar in nature. Let's do something like this. And let's identify the critical point. We'll call this example 3. The critical point is -2. So we're going to find the limit as x approaches -2 of the function. All right. Well, this time it's 0. Yeah. The y value here, again, I like to draw the neighborhood. It's right on the axis, so the y value there is 0. So there's your limit. Your limit is 0. Right? And it is the same, yeah? There's not another point that it's getting close to. So as you get close to 2, the limit is getting close. As you get close to -2, excuse me, the limit is getting close to 0. Now this time it's the opposite. The limit exists, but the value does not, because -2 is not in the domain of the function. The domain of the function are all of the x values. Again, this is your x values that you can insert or plug into the function to get a point. Yeah. We don't typically draw it like this, but every place where you see a curve or a line, those are all technically solid dots. You can imagine an infinite number of solid dots all clustered together. So the domain, you can think of it like a string of pearls where there's infinitely many pearls, and they're all infinitesimally close to each other. All right, and that's what gives us this, curve. But when you get to -2, there's a missing pearl. Yeah, one of them's fallen off the string. And so that means it's not in the domain. There's no x value. There's no y value. That point just does not exist. DNE. The best case scenario, if you like to be an optimist about limits and values, are when the two things agree with each other. Example 4. Again, I'm doing the same instructions for all of these. Given the graph, find the limit. Just changing the critical value. So this is if you think positively, or you want this all to work out nicely, this is what we hope for. 1, 2, 3, 4, 5, 6. So the limit as x approaches 6. And then our y value is -3. All right, so the limit as we get close to 6, as we get near 6, is -3. And then because there's no open hole, although you can think there is an open hole behind this dot. Yeah, behind this dot, there's an open hole. That's kind of what the limit is telling you. So when you're just doing the limit, just imagine sort of like time elapsing. When you've just done the limit, it's -3. But because the hole is filled in with a solid dot, that means that that 6 is in the domain. Yeah, because it's a closed dot or a solid dot. And so the y value is -3. Yeah. So you can think about it like the limit is the hole, and the value is the dot, and the hole and the dot correspond with each other, and so you don't even notice that there's a hole there. All right. Once we get beyond this chapter, maybe not even this chapter, probably just this example, you may not always see the solid dot like that. It would just kind of look like this. All right. That's what a solid dot looks like if we're not exaggerating it, right? Because you got to kind of decide how much exaggeration you want to do. Sometimes we exaggerate that point. Sometimes we'll come over here and exaggerate that point, right? But when you exaggerate a point, you're not changing the function in any way. I mean, these dots are everywhere. It's just whether or not you want to magnify them, right? So if I zoom in on any particular point, well, then that dot becomes magnified. Yeah. But those dots are there all along. All right. The opposite is not true. If I want to show you a hole, I have to use a symbol to represent what the hole is. Yeah, where we call that a singularity, or sometimes an open hole on the graph. Okay, well, one more example that's a little bit more complicated, although I shouldn't really say that it's more complicated. I should just say that it has more parts, that's all. It's the same complexity, just with more parts. So we have some function. It's got a hole. That's terrible. Let me try to draw that better. It's got a hole here. Then it has a dot, sort of way up here. All right, and then it's got another hole down here. And then it goes up to another hole, and then it turns around like that. So this is just, sometimes we refer to this as a Frankenstein function, yeah? Or the formal name for it is a piecewise function. So it's sort of cobbled together by gluing together a whole bunch of parts of other functions. And we'll get deeper into that concept later. So just assume that you've just stumbled across this thing and now you're going to analyze it. All right. So we have two critical values this time. We have -1. The critical values are the x values that we're interested in. They're critical. 1, 2, 3, 4, 5. This looks like 6. So we have two critical values. So let's evaluate the limits. Let's find the limits, calculate the limits. They different, all equivalent ways of saying the same thing. So x approaches -1, and then let's do the limit as x approaches 6. Okay. Again, in chapter 1, I typically tell you where I want you to find the limit. When we get into chapter 2 and 3 and 4, you might not be told where the critical values are. It might be your job to determine those critical values. It should be pretty obvious if the graph is already given. If the graph was not given, then it becomes less obvious where those critical values are. But again, this is chapter 1, so let's just sort of get into it. So as we approach -1, there are two different y values. Yeah, 2 and -4. The limit must be one real number, so that limit does not exist. All right. And we're not really concerned about the dot yet, because that would be the value of the function. We'll get to that in a minute. So just sort of ignore that dot. As you approach 6, however, there is only one y value. So 2, 4, 6, 7. So the limit as you approach 6 is 7. Okay, and then now let's talk about the dot. Evaluate, also known as finding the value. F of -1 and f of 6. So there's a dot. When x is equal to -1, there's a solid dot. Looks like 9, so that value will be 9. All right, and I'm just going to put a little cloud here. It's the point -1, 9. Yeah, that's the point on the graph here, -1, 9. Don't type that in this example, just type 9 because the -1's already there. All right, so this is what's called the function form of the point, or of the value, and this is the ordered pair version. Ordered pair. I try to answer a lot of questions before they become questions, because when you go to type it in, you might have the right idea, you might have the right numbers, but you need to make sure you're using the right format. So in this particular question, we're just doing the value, which is 9. Okay, and other questions I might ask for the point, which would be -1, 9 with the parentheses and the comma and such. And at 6, right, you're going to look all the way down. Look down, look up. Yeah, there's no dot. 6 is not in the domain. Yeah, there's no point. No point at x equals 6. Yeah, so no ordered pair exists. And you might be like, well, what about the ordered pair 6, 7? Right? Well, isn't that an ordered pair? No, it's not. Because in order to be an ordered pair, it must be a solid closed dot to be given an ordered pair. All right? This does not deserve an ordered pair. The limit exists, but the point does not. Okay, so transitioning now to the next topic of this lecture, we can't really fix this part, right? Where points don't exist, right? That's going to happen. That's going to continue to happen where there's going to be values in which you cannot evaluate them at that point. That's going to happen for this entire course, right? But we would really like this to happen less, right? The limit to not exist. We'd like to sort of reduce the likelihood of that happening. And the way we do that is by changing our point of view, right? And so this is a perfect way to transition into the next topic, which is a one-sided limit. So that's where we're going next. One-sided limits. I'll just leave this up here. Leave this here. Yeah. So we don't really need this anymore. So we're going to focus right here. So what we're going to do is whenever this happens, whenever there's a break, it's typically what we call that, a break in the function, where there's two different y values for the same x value. All right. We're going to say, well, maybe we can sort of tweak our definition and approach it differently. For example, if I was looking only on the left side, we could call that the left-hand limit. And then we would write the limit as x approaches c with a little negative sign up here. It looks like an exponent, but it's a negative sign of f of x is equal to, what should we call it? L1 or something? Let's call it L minus. There we go. L minus. Yeah. If, I don't want to call it L because they might be different. Yeah. I might regret that notation. I might change it, but for now, let's just call it L minus. Okay. If f of x is near L minus when x is less than c. All right. It also has to be near, so maybe I'll say when x is near c and less than it. In other words, we're over here. So x is on the left-hand side of whatever c is. This is our c. We'll call that the left-hand limit. And then similarly, the limit as x approaches c from the right of f of x is L plus. And it's going to have the same basic definition. If f of x is near L plus, when x is near c and x is greater than c. So that would be on this side approaching the c from the right-hand side. So those are what we call the one-sided limits. And then we might increase our likelihood, like in this problem, of not having to put DNE. Okay. So let's go ahead, before I erase this, let's go ahead and write down what these two limits would be. Maybe I can just write them up here on the board here. So we have the limit as x approaches -1 from the left of f of x is 2. So that would be our L minus. So we approach it from the left. And then the limit as x approaches -1 from the right of f of x is -4. So as we approach it from the right, the graph is getting close to -4. The y value is getting close to -4. And as we approach it from the left, it's getting close to 2. And then if these are equal, L minus is equal to L plus, then the limit as x approaches c of f of x exists. So now we're getting a little bit more detailed as to what it means to exist. If the left and the right agree with each other and they give you the same value, then this limit exists. I already told you that this limit doesn't exist, so I mean that doesn't change, right? So the general limit doesn't change, but the left-hand limit is 2, the right-hand limit is -4. These two things do not agree with each other, so since 2 does not equal -4, the limit as x approaches -1 of f of x is DNE. So we can't change the fact that the limit doesn't exist, right? That was already determined 10 minutes ago. But we can still talk about limits, right? Once they don't exist, it's like there's nothing to say about it anymore. But if we want to still discuss it, we can say, well, sure, the limit doesn't exist, but the left limit exists and the right limit exists. So that gives us more material to discuss. All right. So for the rest of these examples, let's go ahead and look at some new graphs. Again, this is the graphical approach, so we're always going to start with a graph until we get to the numerical approach. Something like that. So find the limits. The critical value looks like 1, 2, 3, 4, 5, 6, 7. As soon as I write all this down, you can answer them as quickly as I can write them down. All right. So the limit as we approach it from the left. Let's look for the y value. Y value looks like 4. So as we approach it from the left, the y value is 4. As we approach it from the right, I've got so many colors, I might as well. Let's see what happens when I use this color. As we approach it from the right, it's still getting close to 4. All right. So this is our L minus. This is our L plus. Right? And they are equal to each other. So the limit exists. And it's equal to that. Yeah, whatever these are, this now just becomes L. Right, so if the L plus and the L minus are equal to each other, then there's no need to have the superscripts, right? There, you can just call it L now. Right? There's only one limit. All right. However, there is no solid dot. Yeah. So look up, look down. Yeah, you don't see any solid dots, so that means it's not in the domain. So DNE. There you go. So now I don't really have much more, lesson delivery here. I just have lots of different versions of this problem. And you think of all the different things that could happen. So that would be the limits exist, but the value doesn't. You could also have something like that. So we'll call this example 7. This time there is a dot. Let's make sure we identify the critical value, -3. So I better change the question. Give you a second to get rid of the old answers here. A lot of these are duplications of the same format, which means you can pretty much breeze through these. Visually, you pop up the question, you look at the graph, you answer, you fill in all the boxes. Not a lot of calculating to do. So if you're looking for some easy points that doesn't require a lot of work, might as well take advantage of that now. So let's see what the y value is. 1, 2, 3, 4 is the y value. Oh, it's 4 again. All right. Oh, and then there's another y value, -2. All right, so the limit from the left is -2. The limit from the right is also -2. Since these agree with each other, the limit exists and is -2. But this time, because there's a solid dot, there's a point, it's in the domain, the value is 4. Wash, rinse, repeat. Okay, so where are we at? Example 8. What about something like that? Yeah. I should mention, these don't really contribute very much. All of the work is right here in the critical values. So, these graphs could be curves. These graphs could be lines. They could be lines and curves. There's so many different variations on what's happening outside of the critical value. I better change the answers before I screw this one up. Change the critical value. So this time our critical value is x equals 2. So we're going to approach it from the left, from the right, and then generally. Yeah. And then we're going to evaluate it as well. Okay, so from the left, the y value is -3. All right. From the right, the y value is 5. These values do not agree with each other, so the general limit does not exist. But since there is a dot at 2, 1, 2, 3, the value of the function at x equals 2 is 3. All right. One more example, and then we'll stop graphing, and we'll look at numerical approaches, which is kind of like a graph without looking at it. I mean, you get the values, but you don't see the picture of what's going on. So I got one more here. Given the graph, this one's going to be a little busier. Just a little bit busier. Hey, you look familiar. I feel like we've seen this one before. I did change around some of the x and y values, but other than that, it's basically the same question. All right, so let's find our critical values. So this is -1, 1, 2, 3, 4, 5, 6, 7 again. Maybe it is the same. I don't think the y values are the same, though. All right, so let's find the limit as x approaches -1 from the left, the limit as x approaches -1 from the right, and the limit as x approaches -1. So as we approach it from the left, we have 1, 2, 3, 4, 5. Y is equal to 5, or L minus is equal to 5. This is a y value. As we approach it from the right, 1, 2, 3, 4, -5. Okay, these values do not agree with each other. They're not equivalent. They're not identical, so that means the limit does not exist. Okay, but since there's a solid dot, f of -1 is -2 because there is a solid dot at -2, at y equals -2. Since this graph has two critical values, we have 7. So the limit as x approaches 7 from the left. I usually start with the left. That's 1, 2, 3, 4, 5, 6, 7. Oh, it's 7, 7. And you could probably fill out the rest of them now, right? Look. They agree with each other. The two sides are both going to 7, so all the limits are equal to 7. Okay. However, since there's no solid dot, f of 7 is dne. Yeah, there is no point where x is equal to 7. All right, well, that concludes at least this version or this portion of the graphical approach. We by no means are done graphing, but we are going to continue learning about limits without using the graph paper. So this is called the numerical approach. So next, we shall discuss the numerical approach, or the numeric approach. I don't really need to capitalize approach, do I? All right. Also known as numerical methods, and we're going to be using tables similar to the very first example I did when I was talking about the compound interest formula in the introduction lecture. So there's really no backstory to this, right? We're still given a function. But we're not given a graph, all right? So all of the previous examples, we just said y equals f of x, right? And we didn't actually have a formula here. This time we have an actual specified function. It's not arbitrary. And we're interested in the behavior near 3. Now, x equals 3. Now, one of the reasons why we're interested in that is because you can't plug in 3. So notice x equals 3 is not in the domain. Again, I'm not going to give a big long lecture about algebra, but if you recently completed an algebra course, there was lots of discussion about finding the domain. And one of the main rules, or what I refer to as the domain rules, is that you cannot divide by 0. So if you plug in x equals 3, the denominator would become 3 minus 3, and you would end up dividing by 0, and that's against the domain rules. So that value is excluded from the domain. So the domain would be all x's except 3. So sometimes put a slash through the equal sign to say that x does not equal 3. All right. So that means that's an interesting point, right? It's kind of, we've changed the focus now. You know, in algebra, we are interested in finding the exclusions, and then we immediately ignore those values, right? We're like, sorry, kid, you're excluded, right? Well, now we're going to go and discuss the excluded value. So we're going to find or calculate the limit as x approaches 3 from the left, from the right. Probably going to have to erase this in a minute because I'm running out of room. And if these two exist, we're going to ask the follow-up question, what about the general limit? So we want to know all 3 of these. All right, now remember, in order for the third part to exist, in order for the third one to exist, the first two have to both exist and be the same, and then the third one exists, all right? So that's our general question. And we're going to do it by making a table. I guess I could put my table over here. You think I have room? Let's see. So we're going to do x values. I'm probably going to erase this in a minute. So this is just what we're asking. We're going to use the table to help us answer these three questions. And then we're going to plug in the x's. This one will be on the left, and this one will be on the right. So we're going to plug in numbers that are less than 3 here. And we're going to plug in numbers that are greater than 3 here. And we're going to squeeze out the limit numerically. So we'll start with 2.9, 2.99, etc., etc., etc. Probably going to need a bigger table. We're going to need a bigger boat. 2.999. 2.9999. That'll probably be enough. All right, so those are the x's. We're getting very, very close to 3 on the left. On the right, we'll do 3.1, 3.01, 3.001, 3.0001, etc. Gonna need a calculator. So I've got f of x is x squared minus 9 over x minus 3. If you know some algebra, you could probably simplify this, but I'm intentionally not using any algebraic formulas or recipes or techniques today, so I'm not going to mess with this. I'm going to leave it just the way it is. So I'm going to do f of 2.9. I'll leave that to the viewer. If you know some algebra tricks that make this a little easier, that's fine. Although sometimes when you use those tricks, you think you're getting a deal, and then it just ends up screwing up your result. And then you go, shoot, I should have just done it the way Dr. Jordan did it. So I caution you, I encourage you to explore and experiment with things, especially if you remember some techniques from algebra. But I'm going to be getting there eventually, so let's just go at it like this. So 2.9 squared minus 9 is negative 0.59. And then 2.9 minus 3 is negative 0.1. You don't really have to do that on a calculator, right? So you get negative 0.1. And then divide that. And you're going to get 5.9. Positive. Negative divided by a negative becomes a positive. 5.9. All right. You can start guessing if you want, but I do want to see correct numbers. So let's try the next one. 2.99. Some of them are so obvious that within a couple entries, you've already sort of predicted what's going to happen. I know I'm inclined to do that. Sometimes my prediction is right on, and sometimes it's not. I make mistakes too. So 2.99 squared minus 9. I'm starting to see a pattern here. Yeah, it's 5.99. All right, as soon as you're confident, you're absolutely confident. Remember, this is, for now, it's just homework, right? We have several weeks before we get to a test. So you can just say, you know what, I think it's going to keep doing this. 999, 9999, all right? And click submit and see if at least that column is right? Save yourself a little bit of work. It's true, okay? The pattern just keeps continuing itself. The next one will be 0.0059. and then 0.001, and then it'll be 5.999, and so on and so forth. All right, so that's the left-hand one, right? You can kind of predict that it's getting very close to 6. You do have to make a leap of faith here, yeah? 5.99999, it's not exactly 6, but it's approaching 6. All right. Let's see if the same thing happens on the right-hand side. Since this is the first time we've done this, I've purposely selected this problem so that the best thing happens. On the bottom, you don't necessarily need the parentheses, but on the top, you kind of do, sort of. You could probably get away without them, but I use them anyway. So 3.1 squared minus 9 is 0.61. And then the bottom is 0.1, so that's 6.1. All right, so now I have to take a guess. Is it the next one going to be 6.11 or is it going to be 6.01? Well, I don't really want to guess, so you want to guess, go ahead, but I'm just going to do the next one. And then after that, I'll start making predictions and leaps of faith if I'm pretty sure that I'm going to make it. So 3.01 squared minus 9, 0.0601 over 0.01, which is 6.01. Now I'm pretty sure what the pattern is. The next one is 6.001, 0001, and that is also approaching 6. So both sides of the limits are approaching 6. So now we can answer the limit as x approaches 6. Sorry. Oh, don't want to screw that up. X is approaching 3. From the left is 6. The limit as x approaches 3 from the right of the function is 6. All right. And since these agree with each other, the general limit is also equal to 6. So all three limits are equivalent. I will mention that the value at 3 is not 6. Right? 3 is not in the domain. So if I said f of 3, it would be dne. All right? Because you can't actually plug in 3 because 3 is not a valid input for the function. All right. So let's do another one. How about example, what was that, 10? Yeah, so let's do 11. F of x is the square root of x plus 1 minus 2 over x minus 3 again. Sorry, I don't have another. I changed the numerator, but I'm keeping the denominator the same. I really should have picked a different one, but here it is. I'm not going to stop the video now and try to pick up another one. All right, so the same idea. Again, I'm not saying you'll get two that are the same, but that might happen. X equals 3 is not in the domain. Yeah, so that means we cannot plug in 3. It's hard to see. All right. So we're going to go very close to 3 from the left and from the right. Same idea. We're We're going to do 2.9, 2.99, 2.999, 2.9999, 3.1, 3.01, 3.001, and 3.0001. This time the function's a little more complicated, so we got to be a little bit more careful. Instead of squaring, we're square rooting, and we also have an x plus 1 here. So we got 2.9 plus 1. All right. So I'm doing f of 2.9. I like to document which one I'm working on. 2.9. And then I'm going to square root that. My square root button. It gives me a really ugly decimal. It's not really ugly. It's just long. It fills up the whole screen. And then minus 2. Okay, and then I'm dividing by 2.9 minus 3, which is 0.1. Might want to just do that on Scratch so you don't screw up what's on your screen. And you're going to get negative divided by a negative, which is a positive 0.25158. When we have this many decimals, we'll do 6 decimal places. I usually do 4. 2.515823. In this problem, we've got to be careful to round to 6 decimal places. That's highly unusual. I usually go with 4. I think I pre-programmed the inputs on this to go a little bit farther so that you capture more of the pattern. Sometimes only 4 decimals doesn't quite give you the right pattern. So to see more of the pattern, you want more of the screen. So 1, 2, 3, 4, 5, 6. So we're looking here. There's our dictator. You don't really need the rest of them. That number is smaller than 5, so we'll throw that away. We get 0.251582. That's 6 decimal places. Okay. Oh, these are kind of exhausting. There's a lot of calculation here going on. So let's do the next one. F of 2.99. Again, I'm doing all the work on the calculator here. So I've got 2.99 minus 1, or plus 1. Oops, plus 1. That's 3.99. Then I'm square rooting it. Then I'm subtracting 2. All right. And then I got 2.99 minus 3, which is negative 0.01. Oh, I lost my screen here. I got to start over. 2.99. I might go get a nicer calculator. I might just break down this semester and buy a nicer calculator. 2.99 plus 1, square root. I mean, I really like this calculator. It's done me well over the years, but there we go. Very similar number. I don't know if you can see that with the light. There we go. So we're going to get 0.2501564. 1, 2, 3, 4, 5, 6 to look here. Again, that number is smaller than 5, so we're going to throw it away. It's called truncating. And there we go. Can you see the pattern? I don't. It's not quite as distinct as the last one. So unless you can really, see to the next step and see what the next 6 decimals are going to be, it's very difficult to see. So if you don't see it, calculate it. And that's kind of how the numerical approach works. Is just to kind of slog through it. So you get 2.999. Decimal point is kind of fading. And then plus 1, square root minus 2 divided by 0.001. Why do I keep losing that? 2.999 plus 1 square root minus 2 divided by 0.001. Negative divided by negative is a positive 25016. All right, it's actually 0.25000156, but my dictator is greater than 5, so I'm rounding it up to 6. All right, I think I see the pattern. It's going to be 25000. I don't know. It might be a 0. It might be a 1. Yeah. So and now I kind of got to take a gamble. It could, if this is homework, it's not a test. So I probably would just gamble and just put a 1 there. All right, just press submit, see if it's right. If you don't want to gamble, let's stick in the calculator and go. All right, this lecture's already gone over an hour. I want to wrap this up soon. So I'm going to move on to the right-hand side. All right, I'm willing to take the gamble. All right, I think I see the pattern. All right, so we go to the right-hand side, 3.1. So I got f of 3.1. So 3.1 plus 1 square root minus 2, right? Now 3.1 minus 3 is a positive number, so we're dividing by positive 0.1. So I'm going to get 0.248456, etc. So 1, 2, 3, 4, 5, 6, 7 is my dictator. We're going to go up and round that up to a 7. Again, I don't know. I can't quite see the pattern yet. So do another one. Maybe you can. I don't know. I don't see it yet. 3.01 plus 1 minus 2 divided by, oh shoot, I got a square root. 3.01 plus 1 square root, don't forget that square root, then minus 2, then divided by 0.01. They should all look pretty similar. All right, 1, 2, 3, 4, 5, 6. Again, the 9 is going to round this up to a 4. So 0.249844. Do you see the pattern yet? I guess, I'm taking a guess it's going to be 0.25, but I don't know what the rest of it is. But my guess is that they're going to be very similar. Yeah. So I can kind of see the pattern as x approaches 3, f of x is getting very close to 0.25, or you could say 1/4, 1/4 as a fraction. In this lesson, since it's all decimals, I probably would just do 0.25 or 25 hundredths. At some point, there might be some instructions that sort of prohibit you or discourage you from using decimals. So 1/4 would be the fractional answer. One of the reasons why we discourage decimals would be, suppose this was 0.33333333333. Well, then it's very difficult to get that number exactly, right? So in the case of repeating decimals, non-terminating, we like fractions better. But for this particular example, I don't care. These are both equivalent answers. All right, that's the numerical approach. We may do more of these throughout the semester. We sometimes call this the method of exhaustion because it's very exhausting to calculate all these things out. I did leave these for you to do yourself, DIY. That's my instruction, just to finish the problem yourself. I mean, if you want to get all 6 decimal places, because time is running short, I'm going to tell you it's 0.25 and then 4 more decimals. I don't know what they are. I do know that the last line, these things are almost identical, if not exactly identical. Okay, so the last thing we're going to talk about is the wholes, when they're extended to infinity, or the sort of an infinite collection of wholes in a graph, is what's called a vertical asymptote. So back to my graphing board. The classic example is f of x equals 1 over x. Try to draw that. My pen is running out. I have to buy a new pen too for my next lesson. Sort of the classic example of an asymptote. Right. X cannot equal 0. Yeah, 0 is not in the domain. There's a couple different ways to say it. Sometimes I'll say x equals 0 is not allowed, but because I'm also saying it's not allowed, we put a slash through it and say, well, x cannot be equal to 0. In other words, f of 0 does not exist. F of 0 is DNE. Now, the way I was representing this in the previous examples was with a hole. So you can think that, yeah, there's a hole here. But there's also a hole here, and a hole here, and a hole here. And there's a whole lot of holes, right? The entire y-axis is covered in holes. Yeah. And that's a pain in the butt. I mean, every time I have to draw one of these graphs, I don't want to have to draw an infinite collection of holes. And so the symbol that we use, you've seen this in algebra, is just a dotted line. All right. Now, I will warn you, this dotted line is not visible on your screen. I mean, it's visible if I highlight it and make it stand out, but generally speaking, if you open up the assignment, you won't see this dotted line, right? What you'll actually see is something like this. Now, just to make it abundantly clear, I'm going to stretch my scale out a little bit. And I'm going to make that 1 and 2 and 3. -1 and -2 and -3, like that, just to make the graph like a little bit more exaggerated. All right, and then this is 1, -1, and so on and so forth. So what you'll see on your screen is something like this. Forgive my squeak. This is what you actually see, right? Because these are real numbers. The dotted line is just sort of a figment of our imagination. We imagine that there's that dotted line there. I shouldn't use the word imaginary because that has a different connotation, but so this is what you'll actually see. All right. In fact, you won't even see the arrows. It'll just kind of go off the screen like this. The more I mess with it, the worse it gets. So that's kind of the way it looks on the computer. Okay. Now, this gets a little tricky here because we're sort of getting into the deep end of the pool here. And I'm getting sort of the end of my rope on this problem. as we approach 0, from the left, so as we approach 0, so here's x equals 0, as we approach it from the left, the limit is going to negative infinity. Yeah? Now, because negative infinity is not a real number, we don't use an equal sign. So instead of using an equal sign, we say the limit as x goes to 0 from the left of f of x approaches negative infinity. Because you can't say that it's actually equal to negative infinity. Now, I want to point something out. Calculus at this level is notoriously inconsistent, all right? And especially depending on the source that you're looking at. So some sources will actually use an equal sign, yeah, but then they'll put a little caveat or an asterisk or a disclaimer that says it's not actually equal to negative infinity, right? Other sources use the arrow, all right? I'm just as inconsistent, right? If I'm trying to make a point that it's not equal to, then I will use an arrow, right? But if I'm just trying to explain the behavior, right, and it's clear to the reader or to the observer or to the viewer, it's clear to you that it's not actually equal, then I can use an equal sign and kind of go, you know, I'm using an equal sign very loosely, yeah. I will try to be as consistent as possible. So I will say it's approaching negative infinity. It's never going to be equal to negative infinity. But you might see me throughout the course of this semester just say equals negative infinity, but I really mean approaches negative infinity. All right. And I know it's kind of like, what? You're telling me that you're going to be, you know, not consistent? Well, I'm a product of the world that I was, you know, trained in, and the world was notoriously inconsistent about whether we use equals or arrows. Similarly, the limit as x approaches 0 from the right, yeah, we approach it from the right, we get positive infinity or simply infinity. Yeah. And again, it can't be equal. So we say the limit as x approaches 0 from the right approaches infinity. Yeah. And since these two do not agree, they do not agree with each other, yeah, the limit as x approaches 0 is in fact dne. All right, now this example, I haven't even numbered it because it's really just sort of it's breaking open the concept of what we mean when we say does not exist, all right? One could argue that even infinity doesn't exist, yeah? Now you could argue, well, there's no such thing as infinity, so I could put dne here, all right? But because I'm not saying it equals infinity, I'm saying it approaches infinity, this is a valid response. Similarly here, this is a valid response. It's approaching negative infinity. Now, negative infinity and positive infinity are clearly not the same thing. And so the limit generally does not exist. All right. So I hope that's clear. And if it's not clear in just this one, you know, video, maybe it'll become more clear in my next video. So I want to return to another version of the graph. I only have about a minute left. I don't know. I might have to go over a little bit. I don't want to have to film a part 3, so just hang in there, and we'll wrap this up as soon as I can. All right. So that's the idea. Let's do an example. I've kind of lost count. What am I up to? Example 12, maybe? Find the limits, if they exist. So let's do the limit as x approaches 3 from the left. Oh, I'm going to say given the graph. So I'm going to give you a graph. And this is what it'll look like on the screen. All right, I will tell you where I want the limit to be. I seem to be stuck on 3 today. Let's do the limit as x approaches 3 from the right. And let's do the limit as x approaches 3. Okay. So, technically, if you say equal to, all of these things are DNE. Right? None of these limits are equal to any real number. All right. So that's the technical answer, if these are equal signs. So they can't be equal. So instead of rewriting all of this, I am going to switch notations to the arrow. And what I'm doing is I am describing infinite behavior. There are only 2 possible infinite behaviors. All right. As I mentioned earlier, there's dotted line here. Called a vertical asymptote. And it occurs at x equals 3. So x equals 3 is a vertical asymptote. So as we approach 3 from the left, the behavior is going up to positive infinity. As we approach it from the right, the behavior is going down to negative infinity. So I'm just describing the behavior. Yeah. But because these do not agree with each other, I'm going to switch back to an equal sign, and I'm going to say that this limit does not exist. All right. Now I'm using an equal sign, to say that they exist. To say that it does not exist. Sorry, I'm getting tired. All right. What are we going to do? What are we going to do? I guess we'll stop here. I've run out of time. We're going to see more of this in the coming chapters. I'm going to focus more attention on the actual values. Notice I was being very sort of wishy-washy with what the actual numbers were. I used a lot of repetitive examples, but I want to get more into the details of how these things can be different. But this lecture is over. Until we see each other again, I'm Dr. Jordan, and I'll see you on the internet.